It's Paul with a discussion of submanifolds of R3. There aren't too many examples of these in the book because they are tough to graph, but I figured out how to do it fairly well in R. We're going to need two libraries. You will have to install Lattice for wireframe and cloud. Once you've installed it, you have to run it every time. And there's something called scatterplot3D, meant as a statistical function, but we can use it to draw graphs. So let's start by using the definition of a manifold. It is a function graph. And let's think about the unit sphere. Near the North Pole, if we know the values of x and y, we can calculate the value of z. Now, in order to graph this, we need something that is standard when one is using R to do statistics, but that we haven't seen before. It's called a data frame. A data frame is simply a list of columns, and we're going to start by making a data frame whose columns are named x and y. This is actually what is done by the expand grid function that we've used before, but when I say x equals and then give the sequence of x values, y equals and give the sequence of y values, and look at the data frame, I see what we've got. We've got lots and lots of rows, of which only the first 6 are shown, and the columns actually have names x and y. Now, we need to calculate the values in the third column. We specify a column of this data frame G by putting a $sign in between G and the collar name. So when I say G $Z equals the square root of 1 minus G $x squared minus G $y squared, and look at the improved data frame, it's now got in each row x, y, and z values corresponding to points on the sphere. That's what it takes to make a graph. You call the function wireframe, saying z tilde x star y. That means z is a function of x and y. I want an aspect ratio of 1. I specify I want to plot from -1 to 1 in x, y, and z. I want tick marks on the axes, and I'm actually going to get some color on this. Isn't that gorgeous? It's part of a sphere, the part near the North Pole where I can represent z as a function of x and y. Now, to draw the entire sphere, we're going to need lots of function graphs, and I've only figured out how to draw 2 of them at a time using wireframe. I can do that by setting up 2 groups. That's gr equals 1:2. And now what I have done is to set up one group where I take the positive square root to get z, another where I take the negative root to get z, and now I've managed to draw the bottom of the sphere. I'm still not done, though. You can see that I'm going to need to fill in those points, for example, around where x is equal to -1, and in order to do that, I'm going to have to specify x as a function of y and z. To get the points near where y equals -1, I'm going to have to specify y as a function of x and z. And this is the general rule for manifolds. Yes, locally it's a function graph, but at different points you will have to change your definition of which are the active variables, which are the passive ones. Here's a crazy example from the textbook. I'm going to plot x and y going from -2 to 2 and calculate using the textbook's function z is x squared minus 0.2 times x to the 4th minus y squared, and then I just pass it along to yframe and get an interesting looking function. It is interesting in the sense that if you imagine cutting it with a horizontal plane perpendicular to the z-axis, if you go down toward that maximum value, it cuts it in just 2 points. If you move all the way down to the origin, where it looks kind of like a saddle, it cuts it in a rather interesting way. Now let's consider a one-dimensional manifold. For a one-dimensional manifold, there's only one active variable. The dimension of the manifold is the number of active variables. So that means I could pick one variable, say z, as active, and then calculate our passive variables x and y. If I do that and get three sequences, this function scatterplot3d very nicely plots everything and makes a rather interesting picture, a helix that keeps moving up while spiraling round and round. We could also treat it kind of like wireframe, make a data frame with column X, column Y, and column Z, and then instead of calling wireframe, we call cloud with the same syntax, and we get the same helix. You'll recall that in 2 dimensions, parameterized manifolds were the easiest to graph, and it's only slightly more difficult in R3. Now I'm going to try to get the entire unit sphere. I've chosen n equal to 18 because I want latitudes every 10 degrees from the South Pole going up to the North Pole. That means I actually need a sequence of 19 different values for latitude. There they are. And with longitudes every 10 degrees, I need 36 different longitudes running around the Earth. Now what I'm going to do is make a data frame. So I use my parameter values to set up the data frame. It has just columns for u and v. And then from those 2 parameters, I calculate the 3 Cartesian coordinates, x, y, and z, using formulas that you've seen before. And now my data frame has 5 columns. Each row has the 2 parameter values and the 3 Cartesian coordinates. For some reason, we have to convert these last 3 columns to matrices, but you know how to convert a matrix into a vector. You just specify the length. So there are the matrices for x, y, and z. And now if you tell wireframe I want z as a function of x and y, bingo, isn't that beautiful? It's a nice depiction of the parameterized sphere where lines are drawn for fixed values of the parameter. You can try this with other parameterized surfaces. Here's one from the textbook where the parameters are called u and v, and the 3 functions are u cubed times the cosine of v, u squared plus v squared, and v squared times the cosine of u. Again, I convert to matrices. I plot it, and it's a mixed up mess. This is not a manifold because it intersects itself. The plot looks different from one in the textbook because in the textbook for some reason y is plotted vertically, but even when I tried to make it look like that, it was still a mess. Let's try a parameterized one-dimensional manifold. We've drawn a helix before, but the coils were evenly spaced because I was expressing x and y as functions of z. If I express x, y, and z all as functions of t, let's think of t as time, I can think about something that circles around the z-axis while accelerating upward, so that z is not just proportional to t, but proportional to t squared. How do I do it? I start by making a data frame that has just a single column for my single parameter. Then I specify x as the cosine of t, y as the sine of t, and z as t squared. I look at what I've got, a column for the parameter value, a column for the 3 Cartesian coordinates, and now, since these are already matrices, I can just pass them along to cloud and there is my helix, and you can see the coils are indeed getting farther and farther apart. Well, we've done three-dimensional manifolds represented as function graphs, three-dimensional manifolds that are parametrized. What about a locus? This is a really nasty problem because we don't have any particularly good way of generating solutions to an equation of the form f of x, y, and z equals 0. So let's create a sequence that runs from -1 to 1 with point space 0, 0.02 apart, and let's use that for x, y, and z. We've got 101, I guess, points in each direction. So when I call expand grid, I'm going to get a data frame that has roughly 1,000,000 rows. Now, most of those will correspond to points that aren't on my manifold. So what I'm going to do is ask for the subset where x squared plus y squared plus z squared minus 1 is fairly close to 0. I went for 0.05. You can change that if you want. And now you can see I get only a small selection of all the rows. That's a perfectly good data frame. If I ask Cloud to graph it, it takes a little while, but it shows us a sphere. In this case, there's no particular merit in having the points evenly spaced in a grid. An alternative approach is just generate lots and lots of random points. If they're close to lying on the sphere, I keep them. Otherwise, I throw them away. So we'll go for 10,000 of these, set up 3 vectors that will hold up to 10,000 x, y, and z values. And we just keep generating 3 random coordinate values. Check whether the length of the vector is close to 1. If it is, save the values and increment I. And if we have our n values already, we break out of this repeat. That red circle that showed up briefly indicated that R was busy calculating. It was generating lots and lots of points, but we've got them now. Now I'd make them into a data frame, just specifying those are my 3 columns from the data frame. I call Cloud, and again, I get a rendition of lots and lots of points that lie pretty close to the surface of the unit sphere. One of the book's favorite manifolds is the one described by sine of x plus yz equals 0. Favorite, I think, because it's impossible to visualize what this might look like, and also because for any point on the manifold, the first component of the Jacobian matrix is either +1 or -1. It's never 0, and therefore the locus of this function is going to be a perfectly good manifold. I'll do exactly the same thing, set up a uniform grid of points, and now select the ones that lie on this manifold. The red light went on briefly. As soon as it goes off, I can use Cloud, and for what it's worth, there's a depiction of what subset of R3 we've got. This even works if there are 2 constraints. Let's look for the intersection of the sphere with a plane, like x plus 2y plus 3z equals 0.5. I'm only going to go for 200 points here because the probability that a randomly chosen point will satisfy both these constraints at once is pretty small. So I generate 3 coordinates, test, is it almost on the sphere? Is it almost on the plane? If so, I'll save it, and as soon as I've got 200 points, I will quit. If you hadn't seen that red circle before, look in the lower left, you'll see it. It'll take about 10 seconds to generate these points. Sooner or later, I've got them. I make a data frame, call Cloud, and while I don't have that many points, there's enough to show that this manifold is a circle. If you want to improve on this, and it might make a wonderful term project, you can argue, once you found a point on the manifold, then you know how to use the tangent space to find nearby points, or even better, once you found a point near the manifold, use Newton's method to find a point that's right on the manifold. I couldn't find anything in the available R packages that appeared to do this. So if you can do a good term project that graphs a three-dimensional manifold specified by two constraints, you probably got something that may be a first in the world, and maybe you could even polish it up and submit it to the folks that run R.